applying these second laws of thermodynamics to CFTs. So what I'd like to do is just briefly review where we get these second laws of thermodynamics from. They come from what are called the alpha relative Rényi entropies. And so I'd like to review where these come from, some general properties of conformal field theories as they relate to quantum gravity, as well as to the renormalization group. And finally, I'd like to discuss actually the application of the alpha relative Rényi entropy to conformal field theories. Okay. So first of all, we want to know what these alpha relative Rényi entropies are. We're starting from what we're familiar with, which is the quantum relative distance, or divergence, which measures the divergence between two states. If I have a state rho and a state sigma, obviously I can calculate how much these are divergent from this QRD. Trace rho log rho minus rho log sigma. This is a pretty standard way of calculating the difference. One thing that we might, in the same way that the Rényi entropies will be a one-parameter family that generalize the von Neumann entropies, can we generalize this guy to a one-parameter? How can we generalize the quantum relative divergence to a one-parameter family characterizing all possible entropies that satisfy what are called the Rényi axioms for relative entropies? And it turns out there's an infinite number of ways. There's an infinite number of ways to do this because rho and sigma don't commute. So we can slice and dice sigma and rho as many ways as we want to get something that satisfies the axioms that we care about for relative entropies. The standard ones are what are called the quantum Rényi entropy, the QR, which is just looking at rho to the alpha times sigma to the 1 minus alpha. And then a while back, the Mueller-Leonard group and the Wild group discovered an extension to sort of an analytic continuation for alpha greater than 1, which is called the sandwich relative Rényi entropy. But there are many, many, many ways. There's an infinite number of ways to characterize these. There's, in fact, a two-parameter family to characterize all the ways we can make these one-parameter families. So I'm just going to focus on these two today. So that's all well and good, but we also want to talk about the relevance to physics. So we know that there's what I'd call the textbook thermodynamic free energy, which is just E minus Ts. In a quantum system, that would just be the average value of the Hamiltonian minus T times the von Neumann entropy. And we know that transitions are only possible if the free energy, the final free energy, is less than or equal to the initial free energy. This is just textbook thermodynamics. So a while back, there's this famous paper called The Second Laws of Thermodynamics by Brandao, which generalized the regular Helmholtz free energy to an entire family of what are called alpha free energies based on the alpha Rényi entropy. And so he obviously what he does is he just replaces the von Neumann entropy with the alpha Rényi entropy, and now we're looking at the divergence of a given state with the thermal state. So I'm looking at how the state that I'm looking at diverges from the thermal equilibrium state of the system. And now we're only allowed to have transitions from the initial state to the final state if the transitions of all the alpha free energies from the initial state to the final state are less than or equal to 0. So only if all of these alpha second laws are satisfied can I have a transition from an initial state to a final state. So this is a very famous paper, and this has given already several insights into non-equilibrium physics. One question is, how can we, what insights can this give for conformal field theories? So that's what I'm going to be discussing for the rest of the talk. Very briefly, what is a conformal field theory? A conformal field theory is a quantum field theory that's invariant under what are called conformal transformations. So any transformation that will just give me a scale factor of the underlying metric that the system lives on, that's a conformal transformation. These are scale invariant because what I'm looking at is a theory that's invariant under these scale transformations. So these are scale invariant quantum field theories. In some sense, these are the best possible quantum field theories because they're genuinely scale invariant under all transformations of the underlying metric. And it turns out, and I'll get to this a bit later, that these are actually the fixed points of renormalization group flows. So any quantum field theory that we develop are either fixed points or flowing towards a given fixed point in the renormalization group flow. So any quantum field theory that we develop is either a CFT or going towards a CFT in some sense. About 20 years ago now, there's this very famous paper by Maldacena that relates a gauge theory, so any quantum field theory in ADS space, to a given conformal field theory. So I will give you a conformal field theory. You can give me back a gauge theory in ADS space, or vice versa. This is called the ADS CFT correspondence. ADS is a kind of space-time with constant negative curvature. So it's a space-time kind of like the opposite of the one that we actually live on, which if we think of the one that we actually live on as constant positive curvature, so a constant cosmological constant, this is the opposite of that. This is a constant negative cosmological constant. And the reason this actually comes up is because the symmetry group of ADS space is isomorphic to the conformal group in one fewer dimension. Okay, so that's all well and good. So now what we want to do is we want to actually calculate the path integral for CFTs. And we want to ultimately relate these to, we want to ultimately relate the path integral for CFTs to dynamics in ADS, but also we want to relate them to renormalization group flow. So that's what I'm going to discuss for the rest of this talk. It turns out, in terms of Cauchy surfaces, which are these space-like surfaces, so they're Lorentz equivalent to a constant time surface. It turns out that in terms of Cauchy surfaces, it's very, very straightforward. We can model the path integral for the density matrix of a conformal field theory as just flat space with a constant temperature. And then we can look at a globally excited state. So we're looking at this flat space, and now we're universally applying a excited state everywhere on the space. And so we want to know, okay, so this is going to be some excited state of the corresponding conformal field theory. Now, to be able to calculate states out of equilibrium from the ground state or the thermal state, we want to be able to calculate the entropy, the relative entropy between this excited state and the ground state. Well, that's just the trace. So the Bernomonti, Myers, and Oppenheim group, they just discovered that the trace is just equivalent to sort of stitching these two together on a cylinder and running through the entire cylinder and seeing what the value is. So we're looking at the path integral I mentioned earlier of the density matrix to the power of that to the alpha. That's the excited state here, and we're just stitching this together with the rest of the cylinder, which is the thermal state or the Gibbs state. And this, I don't think I have time to discuss some of the details of the ADS CFT correspondence for this, but essentially the ADS CFT dictionary relates a finite temperature CFT to a black hole state. Similarly, the excited state is going to be related to a scalar field in ADS, and then this kind of quenched state, because we're immediately quenching on and quenching off on the cylinder, the excited state. This quenched state is going to be equivalent to a bulk field with sort of time-variant boundary conditions. Okay. For the last part of the talk, I'm going to talk about the application of CFTs to the renormalization group, and then finally I'll discuss the actual effects that we found that have been found for both this quenched excited state and CFTs. And the renormalization group. So just a review for people who are unfamiliar with the renormalization group, we're looking at how coupling constants change, coupling constants of the Hamiltonian change as we change the length scale, either in real space or usually in quantum field theories in momentum space. So the Hamiltonian is going to be dependent on certain coupling constants that show up, that they're the couplings to the actual variables. And now we're interested in how do the coupling constants change as we change the scale of the system, either in real space or in momentum space. We can look at, as an example, we can look at the Ising model here, which is if I look at a system that has just nearest neighbor interactions, if I look at, like, let's say a 2D system with nearest neighbor interactions, now the renormalization step would be to look at, to integrate out or to average out each, like a block of, say, 4 spins or 9 spins, and then look at the new system, the interactions between spins in the new system. So what I'm doing is I'm mapping the Ising model to a system that has higher order spin couplings, which is essentially just a more complicated easing model. And I want to see how do all the couplings in this complicated system change as I continue to change the scale of the system. This is an example of the real space renormalization group, but we can imagine doing this in momentum space as well. So in the coupling constant space, a given Hamiltonian will be represented by a series of points. If I have a couplings, then it's going to be a point in R to the A. And so the renormalization group will map specific points in R to the A to other points. And then I can define what's called a fixed point, which is where the couplings don't change at all, no matter how much I scale the system. And these are called the fixed points. And I can define the change in the coupling constants as the length scale changes as the beta function. There's this famous theorem called the C theorem, which says that, which looks at how the beta function changes as a function of looks at how the beta function changes, and it relates us to sort of a time evolution of a system. And what he discovers is that the fixed point of the fixed points of the renormalization group flow are equivalent to specific central charges for a conformal field theory. So he directly relates this renormalization group flow to the CFTs. And so we can view quantum field theories as points on the renormalization group flow between two different CFTs. And more specifically, we know that he actually gives a direction to this RG flow, that the infrared fixed point of a renormalization group flow will always be less than or equal to the ultraviolet fixed point. So a quantum field theory will always move away from the ultraviolet fixed point and towards the infrared fixed point. Okay, so that's all. So that's all sort of the background. Again, this is a review of what's been happening over the past year. This is all sort of the background to the actual results that have been discovered. So the question is, the initial question was, what conclusions, what insights can these second laws of thermodynamics provide for conformal field theories? And the answer is quite a lot. First of all, the Oppenheim group discovered that there are, if we notice here, the different different relative entropies will give different minima, which correspond to different transition points. So if I'm just looking at this minima here, I'm going to think that there's a transition, there's an allowed transition here, but the other second laws will forbid that. So what we find is that there are further restrictions on transitions between an excited state and a CFT and a ground state, or just two states out of equilibrium. Furthermore, we also discover here, similarly, there are different turning points, if you will, in the relative entropy for the renormalization group. So there are further restrictions on the renormalization group flow from an ultraviolet to an infrared fixed point. So we find these like very, very, very strong restrictions on properties of CFTs based on the second laws of thermodynamics. Ugajan also discovers a relation between these relative entropies and quasi-particle excitations. So this is preliminary work, and we can now so the question is now what are the next steps? My current work is using these results and applying them to what's called the entanglement wedge reconstruction, which is a property in ADS CFT. But another very interesting question for many body physics, especially, which I'd be interested in, but I'm not looking at right now, is the application of these to specific CFTs, especially in like lattice models. And this will give us maybe a lot of insights into examining properties of anyons, which are used in topological quantum computation. So there's a lot. This is quite a lot that has been developed over the past year regarding these second laws of thermodynamics, and there's a lot, I guess, left to do. So thanks.
Questions?
Fashionable buzzword in the